Honors Algebra 2 Pre-Calculus. We're doing section 9.1 in Pre-Calc, which is sequences and series. So let's go over some properties of sums that we see on page 619. So C is a constant in this situation, and I'm going to try and walk you through an example of why some of these things are true, or at least explain like sort of the concept of how they work. So the idea is that, so if I have a C in front of my a sub nth term, right? So a sub I or a sub whatever. So if I have a C in front of this, I'm able to factor the C out in front. So just as an example of kind of what that would look like, right? Let's say I asked you to do the sum from k is 1 to 3 of a 2 times just k, right? Like, so k is that term. The idea is I could either, right, so I could either, and actually we can just call it 2k if you want, so 2k. There are two ways to think about this. I could either do this as just the sum of plugging in 1 to 3 with a 2k, right? So if I just plugged in right into this right now, I'd plug in 1 and get 2 times 1, plus plug in 2 and get 2 times 2, and plug in 3 and get 2 times 3, and I'd get 2 plus 4 plus 6. But the other way to do it is to factor that 2 out, right? I'm going to inch over a little bit this way. And then do the sum from 1 to 3 of just k. Well, that would be a 2 times 1 plus 2 plus 3. And what I want you to notice is that these answers come out the same, right? 2 plus 4 plus 6 is a 12. This would be a 2 times a 6, which is also a 12. So they're the same answer either way I do it, right? So you might say, okay, but Hogan, why on earth would this be useful? So later, moving down the line as we do some other series, right, farther on down in this chapter, you're gonna get some rules for ways to find essentially really easy sigma values for some complicated looking things, and you're gonna kind of memorize a few rules. And you won't memorize a rule for something like 2k, but you will memorize a rule for just k. So by being able to yank that 2 out, by factoring that 2 out of the expression, it's going to be a lot easier to deal with. So that's one. Now the next one is that if you add from 1 to n of just c, where there's no I to plug in, it's just a constant C, it's just going to be C times N, and I'm going to show you why. So let's look at an example of this real quick. Let's say I start at I is 1 and I go to 5, and I just want to add the number 2, just the number 2, nothing else. Well, that means that when I plug in I is 1, it's a 2, because there's nowhere to plug in. And when I plug in I is 2, it's a 2. And when I plug in I is 3, I have a 2, because again, there's nowhere to plug in. And when I plug in I is 4, it's still a 2. And when I plug in I is 5, it's still a 2. Notice that what ends up happening is there are 5 of these. I did it 5 times because I started at I is 1 and I ended at 5. So sure enough, I get a 10. Well, that's just 2 times 5 because I plugged in 2 and 2 and 2 and 2 and 2 5 times, right? Okay. So these two are a little bit more drawn out, and to show you an example would be a little bit longer. Again, this is going to boil down to, at some point later on in this chapter, we're going to learn a couple formulae for different sigmas that are going to basically be shortcuts for us, and being able to split these sigmas apart is going to make it easier to use those shortcuts. But there is actually a logical reason why these are both true, and I can kind of show you a short version of why both of these two are true, just to kind of give you a visual of why they make logical sense. So I'm actually not going to use numbers. I'm gonna show you why 3 is true, because what I'm going to do is I'm going to just sort of show you a sample of what would happen if I plug in the first couple terms here, okay? So let's just say, and actually we can go ahead and do, let's do an example of this, but we're only going to go up to, 3 again, okay? And we're going to plug into a sub I plus b sub I, okay? I'm going to show you what would happen and why I could just split them apart into 2 separate sigmas, right? So if I were to plug in 1, right, I'd get a sub 1 plus b sub 1, right? That would be my first term, right? And then my next term would be a sub 2 plus b sub 2. It's the next term. And then my last term would be a sub 3 plus b sub 3, right? But what I want to show you is if I had written these in a different order, because remember, addition is commutative, right? So I can move these guys around however I want. So what if instead of writing them in this order, I wrote these 3 together, a sub 1 plus a sub 2 plus a sub 3, and I wrote these 3 together, right? So I wrote b sub 1 plus b sub 2 plus b sub 3. Well, wouldn't that be the same as writing that this is the sigma from I is 1 to 3 of a sub I, right? Isn't that what that green stuff is? Plus the sigma from I is 1 to 3 of b sub I. and that was an I, but I didn't do a good job of making it an I, and there's an awful lot of color switching happening. So what I want to point out is now I chose my n as a 3 here, but what I want to point out is that the logical reason that I'm allowed to split this sigma up, right, when I'm doing this sigma right here, you can actually see intuitively why it works if you write it out for a smaller number. Now the subtraction is going to work exactly the same, and I'm not going to plug that one in. The difference with the subtraction obviously is this minus sign, but you'll see that if I were to factor a negative out of that, it would essentially affect all of the b terms. So that's the logic of how these rules work. In terms of having to memorize them, I mean, I don't have them memorized because they seem fairly intuitive, right? The logic is that you can factor out a constant if you're multiplying, and that you can split up sums and differences. But again, that's mostly because sums and differences, well, sums are commutative, and this isn't commutative, but because I could move all the terms around and then factor out the negative, that's the idea behind why it works.